Yeah, hope everybody is fine. Okay, so let me start the lecture. Okay, so in the previous class, we were discussing about explaining the consolidation drain test. So we have seen a couple of conditions like when pore water pressure develops and when we are going to apply the deviated stress until the soil sample is going to fail. So today, one of the most important thing that is consolidated undrained test. Let us try to get some kind of a knowledge and how to interpret the results which you have obtained from the CU test. So first of all, as everybody well aware that when you try to deal with any triaxial testing, so we have to determine the stresses in the form of a total, effective and neutral. So this is when you conduct any consolidated undrained test. So the meaning itself is self-explanatory. Consolidated means initial out allowing the consolidation. So subsequently. So therefore, accordingly, there are 2 to 3 stages. Basically, there are 2 stages. The first stage is during the consolidation phase. The second is during the shearing stage. So if you look at what would happen to the total or effective stress or the pore water pressure at the end of the consolidation. So this is what exactly you are going to initially apply the confining pressure, that is sigma hc is equals to sigma vc, and drainage valve opened. So therefore water will no more take any amount of a load. So therefore the pore pressure is zero. That means no more development of the pore water pressure. So when the pore pressure is zero, it is obvious that the total stresses become effective stress. The total stresses are nothing but effective stresses. Now, during the shearing stage, during the axial stress increase, so what we are doing is, so we are still applying the confining pressure of sigma hc and sigma vc on top of it, keeping the sigma hc is constant, and we are increasing the increase in effective overburden pressure, that is delta sigma. However, the drainage valve is closed. Drainage valve is closed. So obviously, when no water is allowed to expel out from the soil sample, it bound to take some amount of the pore pressure. It bound to bear some amount of the load. So that load bared by the water is called as the pore water pressure. However, so since we are applying the delta sigma herein, that is additional load, therefore the pore water pressure is called as the excess pore water pressure. That means you are applying the additional load delta sigma. Now, depending upon the soil condition, say whether it is normally consolidated or over consolidated, the pore pressure could be positive or could be negative. For example, in case of the over consolidated soil, so the soil able to take the water, that is the positive pore water pressure. Positive means expulsion of water, negative means the tendency to absorb the water. So these are the conditions of the total and effective stresses. So during the shearing stage. So sigma h dash is nothing but the initial total stress plus or minus the increase in pore water pressure. So this is sigma 3 dash. Similarly, sigma 1 dash or sigma h dash, the sigma v dash is nothing but so the initially applied confining pressure followed by increase in the overburden pressure followed by then increase in positive or negative pore water pressure. So this is delta sigma 1 dash. So at the final stage where the sample is going to shear, even at that state also drainage valve is still closed. So therefore the pore water pressure still develops. The pore pressure which develops progressively, it is called as a delta U, and the pore pressure at or during the shearing is called as a final pore water pressure. Final pore water pressure. So therefore, all shearing that is at the final. So introduce a subscript called as a F. F indicates at final or at failure. Okay? Yeah, I'm sorry, there was some problem. So this part I did explain. So this is what is the response in terms of the volume change of the soil sample during the consolidation. So there was a continuous decrease in volume, and this is the stress strain relationship. So for dense sand or over consolidated clay. So as I told you, in case of the dense sand, since the soil particles are already compacted to a maximum possible density state, so initially there is a small amount of compression, then followed by the particles overrolling. Now here, since we measured the pore water pressure, so this is the response of the pore water pressure. So in case of the over consolidated clay or dense sand, initially there is a positive pore water pressure and then followed by the negative pore water pressure. So what is the meaning of this positive and negative pore water pressure? So when you take any over consolidated soil sample, so the particles are packed to a maximum possible density state. When in such a state, they are able to absorb the water. So initially they are able to absorb the water. That is called as a positive pore water pressure. But after some time, so they will allow the water to dispel from the soil sample. So that is called as a negative pore water pressure. Now you have to understand this in a different meaning also. Positive means, so here first of all let me explain the negative. Negative means water is getting expelled out, but at the same time, as the amount of water is expelling from the soil sample, so they equally show the tendency to absorb the water by the capillary action. Okay, so in case of the negative, this pore water pressure is also called as a suction. So here the capillarity, the suction within the soil sample is so high, they could able to absorb the lot of amount of water. While when the pore water pressure is positive, so that means it could not able to take, water is already within the sample. So the sample doesn't show any kind of affinity to absorb the water. So this is in case of the loose sand or the normally consolidated clay, and this is the pore water pressure development in case of loose sand or normally consolidated clay. So I explained the mechanism of why the stress strain behavior is like this for loose or normally consolidated clay, and with a hump followed by decrease in the stress in case of the dense sand or the over consolidated clay. So in the since in the CD test, we did not measure any kind of a pore water pressure, so we did not receive this kind of a diagrams. But in case loose sand, the pore water pressure is always positive. But in case of the dense sand, the pore water pressure initially positive, then followed by the negative. So then how to determine the shear strength parameters? So normally, like the CD test, so we should conduct three test on three identical soil sample confining to three confining pressures. So then draw the Mohr circle diagram, then interpret for determination of the shear strength parameters, that is C and pi. So as I told in the previous class, when you conduct any CU test, you are going to get two sets of shear strength parameters, one set corresponding to total stress and another set corresponding to the effective stress. So here CCU and pi CU U indicates that, so these are the undrained parameters. So meaning thereby, so these were measured without allowing the pore pressure getting dissipated from the soil sample. So that's what is the meaning of total stress. So this is Mohr column failure envelope in terms of the total stress. So then this is since you are allowing the pore water pressure to develop. So then there is a shift to the left direction by the Mohr circle diagram. Then accordingly, So there is a development of the total stress. So then if you try to draw the Mohr-Coulomb failure envelope, then again you will get the C dash and pi dash. C dash and pi dash. So these are the effective stress, shear strength parameters, C dash and pi dash. Cu and pi u are the total stress, shear strength parameters. Although here it has been shown, but we remember that the value of pi dash is much greater than the pi u, and value of C dash is less than the Cu. So this is only indicative, but in reality, so the angle of internal friction increases and the cohesion component decreases. That is in general term. So these are the shear strength parameters that we normally get from the Cu test. Shear strength in terms of the total stress, Cu and pi u. Shear strength parameters in terms of the effective stress, C dash and pi dash. So often the effective stress is also designated in the form of a drained. So cohesion, drained cohesion and drained angle of internal friction. So this is what exact picture. So for Cu develops for sand and normally consolidated clay. So here C becomes 0. When we conduct any Cu test on normally consolidated clay, so now let us look at the practical implications of the Cu test. Cu test. In case of the CD, we understood that for development of the CD, it is a long-term process. So, but in case of the Cu, even this one also long-term process, but this is intermediate. So the consolidated undrained condition arises after the finishing of the construction. Okay, but not in the long term. So if you look at any construction, say for example, embankment is being constructed. So there is a construction phase that is called as a during the construction. Then immediately after the construction, and in the long term. So in the long term. So these are the three stages. So during the construction phase, what happens to the shear strength parameters? And during the consolidation phase, what happens to the shear strength parameters? And after the consolidation, what happens to the shear strength parameters? So initially, so this is the possible shear failure development. So beneath the embankment. Now, when the consolidated undrained condition develops, so try to imagine you are dealing with the construction of an embankment. So, and this is the construction is over. On a subsoil. Once the construction of the embankment is over, now this subsoil undergoes the consolidation phenomenon by expelling the water in the lateral direction on all the sides, both left and right sides. Okay, so when the subsoil is undergoing the consolidation, there is the decrease in the volume, that is in the form of a settlement. Then at the same time, when this soil is getting consolidated, you have to understand that this is not an instantaneous phenomenon. The consolidation is not instantaneous phenomenon. So it happens over a period of time. So therefore, it is possible that when this subsoil is undergoing the consolidation, there is a possibility of the development of the pore water pressure, but at the same time, the consolidation also occurs. Consolidation takes place and the pore water pressure develops. So immediately upon completion of the construction of this embankment, it is understood that the pore water pressure at any point is maximum. You take, say for example, for example this point. So here it is expected in the lateral direction, either in this way or in this way, and the soil is getting consolidated and the excess pore water pressure gets dissipated, meaning thereby the intensity of the pore water pressure keeps on decreases. This is called as a consolidated undrained condition. So the process of consolidation and the process of dissipation of excess pore water pressure both happens simultaneously. Okay. While in case of the CD test, so the in CD test, even though both happens simultaneously, but the strength that we determine is after the entire consolidation is happened. Okay, that means the CD condition arises after the CU condition. If you analyze properly, the CD condition arises after the CU condition. When the CU condition arises, so after UU condition, that is unconsolidated undrained. So I can explain here only. The moment you are putting the load initially, so say for example, this is first phase of the construction. The soft soil is fully saturated. So the moment you apply the load, the soil is under undrained condition. But try to imagine when you are laying a surcharge load on a soft soil, this is not an instantaneous phenomenon. So it takes couple of weeks of a time to finish one surcharge height, say 3 meter or 2 meter or 5 meter. It takes 10 days or 15 days or 20 days or 1 month. Then once the first level of surcharge is completed, so then we try to impose the second level of surcharge load. That means if you look at carefully, the time from the starting of the day of filling to the ending of the day of the filling, it is almost a month or 2 months, depending upon the volume of the earthwork involved. That means up to 1 month or 2 months, the kind of the condition that develops in the soft soil is UU, unconsolidated undrained. Okay. Now say from the day of the filling is over, now the amount of the load, that is delta sigma, the amount of load delta sigma is remained constant, and the density of load is causing the consolidation of the soft clay. So whenever delta sigma is constant, that means a constant amount of load is this condition falls under CD, consolidated drained. So when delta U is 0 means all the water got drained out from that particular area of the soil sample. I hope now it is clear to you all how to distinguish between, yeah.
Sir, please explain again from delta sigma. Your voice broke in between, sir.
Okay,
Uh, when you applied delta sigma.
okay. Okay, so let me explain you first. So you are planned to construct an embankment, say for example of a height of 3 meter. On the day 1, you started filling on the soft clay. Okay, so say you completed on day 10th or say day 15th of one particular surcharge height. So then once this level is completed, then you have gone for further raising, say second raise. Okay, so this is 3 meter, this is 3 meter. So from the day 1, say this took 15 days and this took another 15 days. Say this took 15 days and this took another 15 days. So total 30 days. That means you took solid 1 month time to prepare this surcharge load. Try to understand during this 30 day, is the delta sigma is remained constant? No. So the delta sigma is a variable. Whenever there is a variability in the delta sigma, the kind of the condition that develops within the soft clay falls typically under UU, undrained. Now say after 30 days, so the delta sigma is remained constant. That means This constant amount of the surcharge load is causing consolidation within the soft clay. So this kind of the consolidation typically falls under CU, consolidated undrained. So why undrained? Because the water is still dissipating. So in the process of dissipation, the amount of the pore water pressure gets decreased. Okay. Now once all the water is dissipated, so when delta U becomes 0, then the condition develops is called as a consolidated drained. So no more consolidation and no more drain. Phase, the unconsolidated condition that develops is called as a consolidated undrained. Consolidated undrained. Once all the pore water gets expelled out from the soft soil and the soil undergone the fully consolidation, that kind of condition is called as the consolidated undrained. Sorry, consolidated drained. Okay. Now let me also explain you. Uh, Now we are talking about only the consolidation. But what about the strength or what about the failure? We never talked about the failure. Okay. So now let us talk about the failure condition now. Okay. Now let's see. So as I told you, it took 15 plus 15 days after time. So for filling of the embankment or raising of the embankment two tiers. Now suppose within these 30 days or immediately after 13 days, if this soft soil fails, okay, then this condition is called as a failure or the slow failure under undrained condition. So the parameter, the shear strength parameter, which was shear responsible for slow failure of this kind of embankment is only because of the undrained cohesion. Undrained cohesion. So undrained cohesion. Okay. Now, say for example, there was no failure within 30 days, but there was a failure at 60 day. At 60 day. Then how do you call this kind of the failure? Can we still say that it is UU? No, because there was hoping within the remaining 30 days, there was some amount of the consolidation. That means the CU is no more CU. It was slowly transforming from CU to C dash. But within that, there is a development of the pore water pressure. Pore water pressure. It is obvious that the frictional component is dominating the cohesion component within this 30 to 60 days. 30 to 60 days. So means when there is a slow failure during the consolidation stage itself, then that is called as CU, consolidated undrained. Consolidated undrained, because it is still failed because of the undrained cohesion. Undrained cohesion. Now say the more water within the soil, which might be resulting in the development of the pore water pressure. So since all the water get drained out, consolidated drain slope failure. I hope it is clear to everyone. Now let me also make you understand one of the most important thing, but because most of the people doesn't aware of this one, or neither nobody explains. Say for example, once the construction is over, once we attain the condition called as a CD, consolidated drained, consolidated drained. Now at the CD condition, say initially the groundwater table location is so almost at the greatest depth. Greatest depth. Now during the rainy season, what happened is the groundwater level has increased to this one. Increased to this one. Okay. So we assumed the condition of consolidated and drained. But during the rainy season, the water level rose from far below to the almost near to the surface. Now what is the condition of the soil here when there was a water? Is it still consolidated drained, or is it CU, or is it UU?
Sir, CU.
Why?
Sir, because soil is already consolidated, but
But
now water is present in the soil, so it will take some time to drain it out.
some time to drain it out. Okay, so good. So any other explanation by anyone? See, once you are understanding this point, then you can understand the crux of UU, CU, and CD. Now let me ask another question. So initially, the soft clay is fully saturated. So therefore, the moment you start filling, then unconsolidated undrained condition was arising. Then slowly, because of the delta sigma, that is increase in effective overburden pressure, the soil is transformed from UU condition to the CD condition. UU condition to the CD condition. Now suppose say, so during this UU to CD, the total water got drained out from the soil sample. We could successfully able to drain out the soil sample. Now, when there was a rise of the groundwater table, is there any reversal is possible? Is the reversal is possible? So the way we have gone from UU to CD, suppose if there is a rise in the groundwater level, is a reversal possible?
Sir, I think up to CU is possible.
Yes,
Up
sir.
to
CET to CU.
CU is possible. So UU is not possible at all.
Then you have to reduce that surcharge load.
It's a good, yeah, good point to raise. Suppose even if I remove the surcharge load, so he is saying if you remove the surcharge load, then we are going to get the UU. So others, so can any of you throw some light on this?
No, sir. If we increase the load, then it will con-
Is
come under
consolidate
unconsolidated.
is consolidation is a reversible phenomenon
No, sir.
even after removing the load?
No, sir.
No, sir.
No, sir.
But if we increase the load, it will consolidate again for that particular load.
See what is the basis for saying that it's
Sir, because the delta sigma will increase. So
no. My question is, see, you try to understand. When you draw the consolidation graph between applied stress versus the change in wire ratio, it is a linear relationship. I hope you understood.
yes, sir.
So this is applied load and this is wire ratio. So this is a linear relationship. That means you keep on applying the load, there is a decrease in the wire ratio. The moment you release the load, then they should achieve the initial state. Is it true?
No, sir.
Why?
because after getting some load, soil is rearranged. Soil particles are rearranged.
Okay. So they will
That's
not
why they
rebound.
will not go the initial state, but yes, the void ratio will again increases, but not the initial state.
So there
They will
will be
not.
some rebound, but it will not reach up to initial void ratio.
That's true. So there is a small amount of the rebound, but it will not reach its initial state of the condition. Meaning thereby, when you consolidate the soil sample from UU to CD, so you can easily achieve UU to CD condition, but it is not reversible. You cannot come from CD to UU. Once the soil sample is consolidated, so it is like your plastic deformation. Plastic deformation means irrecoverable. Irrecoverable. That means whatever the consolidation that took place, even if you remove the load based on this consolidation graph, even if you remove the load, there might be a small amount of the rebound, which may be significant, may be insignificant, depending upon the soil type. Soil type. Okay. So if there was no rebound, then obviously there cannot be any kind of a condition of UU. Okay. Then when you talk about from CD to CU, first of all, there is no possibility of the consolidation at all. Okay, so there is no change in the consolidation aspect. While regarding the drainage condition, yes, to some extent, so the drainage D may become U, but not to the fully. For example, uh, amount of UU at CU condition and amount of U at D condition, if you compare this and if you compare this, so it will not completely achieve the undrained condition because the soil is fully consolidated. Is that? See, you are achieving undrained condition to the drained condition depended on the permeability of the soil mass. That is the reason your all consolidation equations are as a function of the K. If you remember, your CV is equal to K by gamma W. Okay. CV is equal to K by gamma W. So your consolidation is also an inherent function of the permeability. But permeability is directly proportional to the void ratio or the density of the packing of the particle. So more consolidated means more permeability or less permeable. Less permeable. Since the soil is already consolidated, we can't expect much permeability. So of the soil where the consolidation took place. So when the permeability is low, so even if the groundwater table rises to ground surface, so we can't expect that this entire volume of the soil mass is again fully saturated. It may or it may not, depending upon the K value and depending upon the consolidation that took place. So therefore, there is a small degree of the reversal from CD to CU, but not complete. Okay. So because of this small degree change, so often if there was no such charge, this condition becomes more prevalent. This is one of the reason whenever you construct any embankment using the surcharge load, but after removal of the surcharge, if you don't construct a permanent structure on top of this consolidated soil, then after if you give a long gap between the removal of the surcharge and the construction of the superstructure, and after long gap you build a superstructure, there may be possibility of the failure again. That's why we should not give a huge gap between the CU and CD. Meaning thereby, once the soil sample has been consolidated, so by applying the delta sigma or surcharge load, you should immediately build permanent structure on top of the consolidated soil sample, so that there can't be any change in E and any change in the permeability. So therefore, the CD condition is maintained always, so that the soil exhibits maximum shear strength always. Okay, so this is the logic of your entire CU, UU and CD. So once you are understanding this crux of the UU, CU and CD, then you are understanding So everything is governed by how soon you are imposing delta sigma, either temporarily or permanently. So if you have any questions, you can ask me. So this is in case of the rapid drawdown. So on earth dam. So initially it was a fully saturated, but there was a rapid drawdown. So the amount of the time required for lowering of the groundwater table is not sufficient for soil particle to allow the drainage. So therefore, so there was water held within the soil particle. So here you can say it is not the undrained condition, but rather it is the increase in weight because of the water is trapped already inside the pores. So that causes sometimes failure. And why it is consolidated undrained? Because the embankment is already consolidated. So the rapid drawdown will not happen the soon after the construction of the embankment. It happens after some time. So then rapid construction of an embankment and a natural slope. So this also leads to the consolidated undrained condition. So then the last one is the unconsolidated undrained test. So here no drainage valve is opened, no soil sample is allowed to consolidate by applying any amount of the confining stress or the deviator stress. So here when you apply the confining pressure, so that total load is shared between the soil particle and the water. So because the excess pore water pressure develops within the soil particle. So here since no water is allowed to drain out from the soil sample, obviously we can able to see the again change in the volume of the soil sample, but in a reverse direction. So initial volume of the sample is A naught into H naught. So no drainage, specimen condition during the shearing. So sigma 3 and sigma 1 is nothing but sigma 3 plus deviated stress delta sigma. So volume of the sample during shearing A into H. So since the test is conducted under undrained condition, so your the volume remains same. Volume remains same. So if you multiply or equate both the volumes, then you can able to compute how the sample area, the cross-sectional sample of the area is increasing or decreasing as your program load. Okay, so the change in area is nothing but initial area divided by 1 minus applied strain. The soil sample, so therefore everything is 0. Then you are applying the confining pressure, so both sigma 1 and sigma 3 are remain same. So after application of the hydrostatic self pressure, no drainage, so there is a development of the pore water pressure within the soil sample. So then sigma 3 dash is nothing but sigma 3 minus delta UC, and sigma 3 dash is nothing but both are same. So this is during the hydrostatic, when sigma 3 is remained same in all the direction. Next what we do, so now, so this is the Skempton who try to determine how much is the development of the pore water pressure because of the application of the consolidation pressure or the confining pressure. So Skempton has tried to relate the pore water pressure parameter with the applied confining pressure. So there are two stages here. One is when sigma 3 is applied exclusively equally in all the directions. So sigma 3 is remained constant, but sigma c in the vertical direction, the sigma 3 plus the deviated stress applied. Then what will happen to the delta sigma? So this is when there is a hydrostatic condition. So the relationship between applied confining pressure and the equal development of the pore water pressure is related with the parameter called as a B. B is one of the pore water pressure parameter. So B is defined as what would be the increase in pore water pressure for an applied cell pressure. So this is increase of pore water pressure due to increase of the cellular pressure. So again, as I explained you, This is called as the excess pore water pressure or increase of pore water pressure. Remember, because this excess is because of the delta sigma. We are applying the, we are imposing some additional load. So increase of cell pressure. Now, why B? Suppose you might know that if B is equals to 1, the sample is fully saturated. That means the entire applied confining load is taken by only the water particles. So this is what is the meaning of B is equals to 1. Okay, you are decreasing the value of B. So what happens to the pore water pressure? It is least and least. Now there is also, if the soil is fully saturated, then B is equals to 1. That is, the entire confining load that is applied on the soil sample is borne only by the water molecules. So no amount of the load is going on to the soil particle. So this is what is the meaning of B is equals to 1. Now during the application of the axial load, so you already applied the delta sigma 3. Then you are going to shear the soil sample by applying the deviated stress, that is delta sigma d. So then, there is already initially the small amount of the pore water pressure. Then when you apply the delta sigma d, there is further increase in the pore water pressure. So C designates the development of the pore water pressure because of the confining pressure. D designates development of the pore water pressure because of the deviated stress. So correspondingly, so the effective stress can be calculated. So this is total minus the pore water pressure during the cell pressure plus or minus pore water pressure during the deviated stress. Same thing, sigma 1 is equal to sigma 3 plus delta sigma d minus delta uc plus or minus delta ud. So here again, the way we have correlated the delta uc with delta sigma 3, then we can also correlate what would be the development of the pore water pressure, so with the imposition of the deviated stress. So these two are related with the parameter called as a A. So this is increase of pore water pressure due to increase of deviated stress. And this is increase of deviated stress. This is content pore water pressure parameter. Okay, so this is step 2, we got it. So the increase in pore water pressure because of the increase in confining pressure, and on top of confining pressure again we applied the deviated stress, which resulted in the further development of the pore water pressure. So that is read in the form of a pore water pressure parameter K. So the total pore water pressure parameter, the total pore water developed within the soil sample is the summation of the pore water because of the confining pressure plus pore water because of the deviated stress. So if you substitute all these things, so then you will get this kind of a relationship. Okay, so just try to rearrange the terms. Then we will get delta u is equals to B into delta sigma 3 plus A into delta sigma 1 minus delta sigma 3. So this is Stanton's pore water pressure equation. Calculate the pore water pressure during the cell pressure application, during the deviated in the final stage. Or what would be the total pore water pressure because of the cell pressure plus because of the deviated stress. So delta sigma d is nothing but sigma 1 minus sigma 3. So this is another analogy. So where we have taken the soil sample, so the pore water pressure is negative. Negative meaning there, negative means this is one of the important points that you have to remember. When the vertical and lateral stresses are becoming zero on the soil sample, how the soil sample could able to retain its geometry? This is a big question. Okay, this is a big question. So this retention of the soil geometry is exclusively because of the negative pore water pressure. So this, because of this negative pore water pressure, or another way of understanding this simple logic is, so this is nothing but your capillary force or capillarity. So the soil sample able to withstand itself because the capillary forces are acting among the particles and thereby retaining the geometry of the sample. Now same thing happens. Just to make a small demonstration, you try to take a sand sample. When you add a small amount of a water, we can able to make a sand castle. Just try to imagine making a sand castle without water. Is it possible? Can we able to make a sand castle without adding a water?
No.
No.
No, sir.
So no. See, but if you take out the soil or that sand sample, and if you take it to our technical analogy, where on the sample this sigma 3 is 0, sigma 1 is 0, but still the sample could able to retain its geometry. So that is because of this capillarity or the capillary pressure. But here it is termed as the negative pore water pressure. So therefore, consequently, if you transform everything into total stress, your sigma h dash is nothing but your the pore water pressure or the capillarity pressure. So sigma h dash or sigma v dash is nothing but so the initially existed negative pore water pressure within the soil sample. So this is most important in case of the UU test. In the hydrostatic cell pressure, that is sigma 3, there is already some amount of the capillarity pressure, that is a negative. Of it, you are applying the pore water pressure. Okay, so here you have to understand, initially it could be negative value, So because of this negative capillarity, the soil particles are holding themselves. But what you are doing on top of it, you are applying the hydrostatic or the confining pressure. When you apply the confining pressure, it will try to overcome the initial capillary action. Then only it could able to break the soil sample. Without overcoming this initial negative capillarity, the applied sigma C cannot able to shear the soil sample until and unless it overcomes the minus UR. Okay, so that means when you are applying the sigma 3, it is initially tries to overcome, then convert the negative into the positive. So if the soil sample is fully saturated, Rp is equals to 1. So this is negative plus sigma C. So this is a final condition. So delta sigma H is nothing but UR, and sigma Vc is sigma C plus UR minus sigma C. So again, same. So the positive capillary pressure. During the application of axial load, so initially there exists the negative capillarity, then you try to overcome this negative capillarity by applying the confining pressure. That means now from negative capillarity to the positive capillarity at the positive pore water pressure. So on top of it, again you are applying the delta sigma. So therefore the final or the delta U is because of delta sigma. So this is what is the final condition. So the sigma H dash is nothing but sigma C plus UR. If this is UR minus sigma C and plus or minus delta U. So sigma H dash is nothing but sigma C minus delta U. So minus it will become plus. So plus minus it will become minus. And this is plus or minus or plus. Similarly, plus sigma V dash is equal to sigma C, that is confining pressure, minus this is sigma C plus delta sigma C minus delta UR, minus becomes plus, so plus UR, and minus into plus, it is minus, that is minus sigma c, and this is becomes minus r plus delta u. Okay. So this is at failure. So this is at failure. So almost I will cancelled out, will get cancelled out. Then whatever remaining is, so delta sigma f. So Mohr circle in terms of the effective stresses do not depend on the cell pressure. So since sigma c got cancelled out, so the effective stress will be independent of cell pressure. So in UU test. So therefore we get only one Mohr circle in terms of the effective stress for different cell groups. Okay, so that's why no more total stress Mohr circle in case of the unconsolidated undrained test. Only one circle. So what here you can see, yeah, same thing, only one circle, and the failure envelope. So only cohesion component. There is no frictional component. So undrained friction is 0. There exists only the undrained cohesion. Undrained cohesion. So this is effect of degree of saturation of the failure envelope in case of undrained. So what happens if the sample is not fully saturated? So suppose if you look at when the sample is fully saturated, so it indicates that the load is borne only by the water particle. Because the pi u is 0. The meaning of the pi u is 0 means the particles will not bear any amount of the load. But if you do not maintain the degree of saturation of 100%, then you get this kind of a response. This is one of the fundamental reason. When you do your UU test, you always get increase in Mohr circles. Okay, so the fundamental reason for you getting the 3 different Mohr circles is you are not maintaining the degree of saturation of 100%. Okay, so if you maintain SR is 100%, so it is irrespective whether you modify the sigma 3 or not, you will only get the Cu value. You will never ever get the pi u value and pi u value. So these are the applications of the UU. This already explained. I will just simply skip it out. So this is during the construction. So UU condition develops during the construction. Embankment constructed rapidly over a soft clay. After the construction, it is Cu, then followed by the Cu. So then same thing in case of the at the dam also during the construction. So the unconsolidated undrained condition develops. Undrained shear strength of the clay. Then similarly footing. So initially, so undrained condition develops. So as the delta sigma is remained same, that lead to consolidation of the soil sample, leading to Cu development of the Cu condition. Then once whole water get drained out, so then it further leads to CD condition. So UU test simulates the short-term condition in the field. Thus Cu can be used to analyze the short-term behavior of the soil. But try always to remember, UU is the worst condition possible. UU is the worst condition possible because the amount of the load shared between water and the soil always volatile. It is a dynamic process. It is not a constant. As the water keeps on getting expelled from the soil sample, soil particles try to bear more and more amount of load, and the water bears least and least amount of the load. So in case of the CD test, this dynamism is completely absent. only the soil particles bear the total amount of the load. So when you talk about only the soil particles are bearing the load means it is only because of the frictional component. Okay. So when there is a load sharing means, so it is the cohesion component plus it is the frictional component. But in undrained condition, as we have seen in the couple of slides back, the pi u is completely zero when the sample is fully saturated, meaning thereby the soil will not take any amount of the load. It is only the water particle which takes the load. Okay. So this under this undrained condition, so as the water cannot able to bear the load for longer times, so it exerts some kind of excess pore water pressure on the soil sample in the lateral direction. Suppose when it is exerting say for example, when it is exerting the excess pore water pressure in the lateral direction, suppose if this overburdened soil is not able to resist or the failure is imminent. So this is the reason. So the UU becomes worst. While CD condition, it is the safest. So this is the last one is unconfined compression test. This is very simple. So unconfined compression itself, there is no confinement in the lateral direction. Rather, you are compressing the soil sample only by applying the delta sigma. So sigma 3 is 0 and sigma 1 is nothing but only the deviating stress. So this is the soil sample sheared only because of the so from the unconfined compression test, sigma 3 is 0. Okay. Now I can make a correlation between the negative UR that I was explaining during the UU test with this. So when you compact the soil sample, so this soil sample is held in its geometry by the two mechanisms. One is because of the compaction energy and the second is because of the negative pore water pressure. Okay. Since we can do only one test on a soil sample, so we will get only one Mohr circle. Since sigma 3 is 0, so the meaning of sigma 3 is 0 means it passes through the horizon and this is normal stress. So try to draw the Mohr circle. What you get is the unconfined compressive strength. So unconfined and Cu is nothing but Qu upon 2. So half of the total unconfined compressive strength. Okay. Yeah. So these are the most, this is small interpretation or the summation about the triaxial testing. So triaxial testing. Suppose when you are conducted CU test, say for example, start from the UCS, UU, CU and CD. So let us try to understand which one will give you the least amount of the strength of the soil and which one will give you the highest amount of the soil. So can anybody throw a light? Hello. So this is the diagram it is showing. As you are increasing the cell pressure, so there is increase in the normal stress. So let us go for the different reaction. Hello.
Hello.
Yes, sir.
Yeah. So this is a small summary about different triaxial testing. So if you look at carefully here, so the UCS will give you the least amount of the soil strength, then followed by the unconsolidated undrained, then consolidated undrained, then consolidated drained. Okay. So can anybody able to explain, see, how for the same soil the strength is improving? We did not change the soil sample, but even then, how the strength is getting improved?
Sir, because the dependency on friction factor is increasing and cohesion is reducing.
Friction factor is improving. Okay. So any explanation from anybody?
The rearranging of the particles is more in case of CD. So the frictional component which contributes more on the shear strength, because
Okay.
C is constant. So sigma is increasing, so that the sigma tan phi value is increasing.
Okay. Okay. So others are not talking at all. I don't know whether they are there or they went somewhere.
So because of increase in effective stress,
Because of increase of effective stress. Okay.
Excess for water pressure is reducing, so effective stress increases.
Okay. Good. Good. Okay. So this is another summary about different testing conditions on different triaxial testing. Okay, so this is small compilation. So when you conduct UCS, you get only the undrained cohesion. Undrained cohesion. So I don't need to explain again why it is undrained. Okay, so here sigma 3 is 0. So sigma 3 is 0. So therefore it is the Mohr circle is passing through origin. So next comes is unconsolidated undrained test, and this again depends on two things. So are you maintaining the degree of saturation of 100%? Then what you will get is only the Cu value. You will never get so the pi u value. That is undrained friction angle is 0. So if the sample is fully saturated in unconsolidated undrained test. Suppose if you are not maintaining the degree of saturation of 100%, so then you are bound to get so the Cu value and the pi u value. Cu value and the pi u value. Okay, so then in case of the Cu test, so there is a consolidation process, then followed by the shearing. So there is a transformation of the stresses from total to the effective. Total to the effective. So obviously there is increase in the friction and decrease in the cohesion. While when you conduct any CD test on any soil sample, it is immaterial whether it is a clay or sand. So the Mohr-Coulomb failure envelope always passes through horizon. Always passes through horizon. So therefore, what we get is only the angle of internal friction. Angle of internal friction. So this CD graph is valid again. I repeat. So valid for Koizu soil or the sandy soil. It is immaterial. It is immaterial. So that means under dry condition, almost every soil behaves like a frictional material. The meaning of this one is under dry condition, every material behaves like a frictional material. So this is what is the interpretation that can be made from the CD. So the frictional component is, therefore there is highest strength during the CD test and the least strength during the confined UCS. During the UCS. This part I will leave it. So this is all about ray axial testing. So let me take a couple of questions before I start the another thing. You can ask me as many questions as possible.
Sir,
Yeah.
Sir, if we are going to construct something on a barren land, matlab it means no construction has been done on that land since past.
Okay.
So we will go for UU test there.
So barren land means, see again that depends upon whether there was a water or there was no water. Okay.
Okay, sir.
Suppose if there was a water, then you have to go for all these consolidated drained, consolidated undrained. So in its entire life, if you feel that the water will not come at all, then we can go for even UCS also. That will be sufficient.
Okay, sir.
Yeah. So any other question?
So I have a question related to Mohr circle.
Yeah.
If in Mohr circle, if you take any plane and shear stress comes out to be positive or negative, what is the
Okay.
meaning of the sign there?
Positive negative means if it is in clockwise direction positive, anti-clockwise direction negative.
On that plane?
On that plane, yeah.
And with respect to the center of element, right?
There is nothing like that. Center of the element, or at least it is acting on the element. Suppose if you take different elements all along the failure plane, so there is no center. The center is only the center of the circle.
Okay, so let's say we have a center in between the particle, in between the element,
Yes.
and I get a positive shear stress,
Yeah.
let's say at 30 degree from the vertical.
Okay.
If that 30-degree plane is above the center of the element,
It won't go like that. See, for example, you take an what example I can take? Okay. Let me take in this example only. Okay. So here, suppose you take. See, I'm taking one element here, one element here, and one element here.
uh,
Does it make any sense? Yeah. See, the kind of the stresses here are different, and the kind of the stresses here are different. So, for example, if you look at the element here, all the stresses are only in the horizontal direction.
okay,
Okay. But if you look at here, the element itself is in inclined position.
uh,
Okay. And the stresses also in inclined direction.
mm,
So similarly, of course, this and this is same. So we do not know whether this condition becomes critical or this condition becomes the critical. So, and if you look at the development of the failure plane, we always say it always initiates at one point. We do not know where that point. So the
okay,
entire failure plane will not develop instantaneously. So it is a progressive. So it initially starts wherever there is a maximum stress and least resistance. Then slowly it progresses until the entire failure plane gets developed. However, you cannot say that from the development of the one point and to reach this failure plane to the top, it won't take much time. It won't take much time. It can happen in couple of hours and in couple of days. Okay, so therefore we should strictly avoid, first of all, the development of the failure point at any point all along the failure plane. Once it is mobilized, this way it's called as a mobilized cohesion and mobilized angle of internal friction. We should ensure that there is no mobilization of the friction or the mobilization of the angle of internal friction. Once it is mobilized means, so the failure is imminent. We can't able to avoid. But if you able to recognize in between, then we can go for the measures. Avoid it one. So before the development of the full failure plane.
Okay, sir.
Sir, you said that if the ground is completely dry and the chances of getting water coming there is very low, we can even go for UCS.
We can go for UCS aram se. You
But
don't
sir,
need to go for.
if we are going for UCS there, the shear strength which we will get will be very low through UCS.
That depends again your density, not CD.
So the value which we'll get depends upon the density of that soil.
Correct.
Okay.
So any other questions?
Sir,
Yeah.
sir, in the example of that embankment, when the groundwater table was rising in the rainy season,
Yes.
sir, suppose it has risen to the just below 1 or 2 meters below the embankment,
Okay.
and it was CD earlier.
Yeah.
So then it should fail immediately when the groundwater table will rise.
It should fail immediately.
Yes, immediately or just within short span of time.
Uh, why? Why do you think it should fail immediately?
Sir, because shear strength is a function of effective stress, and effective stress is going to reduce when groundwater table will rise.
And what about the consolidation is done? There was already soil got consolidated now.
Yes, sir.
So if failure plane has to happen or the failure plane has to develop, first of all there should be some consolidation has to happen now. Consolidation means settlement. Without settlement there is no failure.
Yes, sir.
You got my point?
Yes, sir.
So consolidated drained CD means no more consolidation or the no more settlement is possible. So this is possible when the groundwater table is at further depth or at the ground surface. So the rise in doesn't affect there. Because it
Can you
won't
repeat?
increase. Okay. So see, say for example, the the soil has already attained the state called as the CD.
Yes, sir.
Okay. So what is the meaning of CD? The soil has attained or undergone maximum possible settlement. No more settlement is possible.
Okay.
When no more settlement is possible, is there possibility of the development of the failure plane? Now, let us look at your bearing capacity theory because you understood this one. When you analyze the bearing capacity, you analyze for two conditions. One is for the settlement next is for the shear strength. But you prefer to do it for the settlement rather than the shear strength, because unless there is a settlement, there is no development of the shear strength and there is no failure at all. Okay, but is the settlement is completely zero ever since the load is applied? No, that's because the particle, suppose if you recall your elastic settlement or the consolidation settlements, so elastic settlement will happen immediately. That means because of this elastic settlement, there is a small amount of the shear strength on the soil or shear stress on the soil. Okay, but which is much lesser than the shear strength of the soil. Therefore, there was no failure. But suppose once the elastic settlement is over, do you expect still there is an increase in the shear stress?
No, sir.
No. Okay, so that means the shear stress is remained constant. That is in case of sandy soil. Let us take the clayey soil. So initially there is elastic settlement, then followed by the consolidation. Since the consolidation is a slow process, so the shear stress imposition on the soil so is very slow. Okay, so since it requires a sufficient amount of time the soil for the settlement, so it takes little amount of time for the failure plane to develop. Okay, but if there is no settlement, there is no shear stress on the soil. And so when you have also understood from your effective stress analysis. So the effective stress implication is, so when the groundwater table is lowered, the effective stress increases. This is what you read. This is what you read in your soil mechanics. Okay, so when the groundwater table is lowered, so effective stress increases, and thereby there is a settlement. Once this process is entirely completed, then you are again seeking that is the process is reversible. So that's what I explained. It is not reversible. No more settlement is possible. So therefore, no more the failure is possible. I hope it is clear to you. Or still there is a
Yes,
question.
yes, sir. It is clear now.
Oh. No, if it's not clear, you can still ask me. There is no question. So any other question from anybody?
Sir, so that we can say that there should not be any movement between the soil particles, then failure will not happen.
Yeah, obviously, nah.
Hmm.
Once CD is attained, it is the soil will not respond whether the groundwater table lowers or rises. How many number may be the cycles of increase or rise or fall of the groundwater table? So it won't affect the consolidation process because the superstructure load is still remained on the soil sample and it is already caused a maximum settlement. So therefore, no more consolidation and no more increase in shear stress possible. But rather, you have to understand one thing. When I talk about all these things, you should uh, earmark two areas. One is right below the superstructure, one is right adjacent to the superstructure. So whatever I said is valid only right beneath the superstructure. But what will happen to the right adjacent to the superstructure where there was no delta sigma at all? There the soil undergoes this entire cyclic process. Cu, Cd, Cu, Cd, Cu, Cd. So that is why the natural self consolidation process is a cyclic process. You cannot say that once the soil has settled to this intensity this year, it won't undergo next year again consolidation. No. So it slowly undergoes the consolidation. It is a cyclic process. But when you keep the delta sigma, that is when it is over consolidated slate, you are stopping that cyclic process. That's it. Good. So any other questions, please? Can I go ahead?
Yes, sir.
Good. So I hope at least I could give you small knowledge about the triaxial testing. So at least it's a hope it is much better than your undergraduation level. So another component of the triaxial testing is the stress path. Stress path. Okay. So this is one of the convenient way of delineating the information from the triaxial testing. Because all said and done, what we have dealt with is only sigma 1, sigma 3, pore water pressure, so on and so forth. But if you look at the in reality or in the field condition, we have read something like a stress history. Then what happens to the stress history as the load is progressing or as the pore water pressure is increasing or decreasing. So the very convenient way of understanding how the stresses will develop and how the failure plane develops within the soil mass is called as a stress path. So the definition of the stress path is the line that connects a series of points, each of which represents a successive stress state experienced by a soil specimen during the process of a test. Now, so far, what we have done is we have conducted the triaxial testing on identical soil samples, and by increasing the increasing the confining pressure. So, for example, if you take 3 cell pressures, obtained the 3 Mohr circles, and we also developed the Mohr Coulomb failure envelope. Okay, so based on these 3 circles, then we said that when the stress is reaching the Mohr Coulomb failure envelope, the failure is imminent. But what process or what path the stress is following, we did not understand. Let us try to understand. When you are increasing the cell pressure, is the stress is following any specific path, or it is just like happening. So we will try to understand a small glimpses about all these things. But for this, to understand the stress path, you need to convert the sigma 1, the major and minor principal stresses, in the form of another parameters. Those are called as a P dash and Q dash. So P dash is the radius of the circle, sigma 1 minus sigma 3 by 2. This is also nothing but shear strength. Then this is the average one. So this is the distance from the origin of graph to the middle of the circle, sigma 1 plus sigma 3 by 2. So this is another designation. So Lambert in 1964 suggested a new coordinate system of P dash versus Q dash. So this is the ideal way of this understanding is converting the Mohr circle from circular state to the linear state. So when you talk about the P dash and Q dash, we no more talk about Mohr circles. But their equivalency in terms of P dash and Q dash. So this stress path is drawn in several forms. That is sigma by stress upon strain space, or principal stress space, or there is a T dash S dash space, or P dash Q dash space. So we can draw the stress path in any of these forms. But in our subsequent slides, we will follow P dash Q dash space. So this is what is exact meaning. So I'm taking the simple Mohr circle diagram. So where sigma 1 is known and sigma 3 is known. So this is a normal stress and this is the shear stress. So you take any point A and any point, so, and you know the radius of this circle is nothing but sigma 1 minus sigma 3 by 2, and the distance from horizon to the middle of this point is called as sigma 1 plus sigma 3 by 2. So these are rewritten in the form of a stress points, So that is sigma 1 P and Q. This P and Q can again be represented in total stress form or effective stress form. Okay. So this is stress point, any point on the Mohr circle. Now, so for better understanding, so say for example, this is one Mohr circle and this is another Mohr circle. Okay. So you try to join one point with the another point, and this line is called as a path. While this path could be linear or could be non-linear, depending upon the total stress condition or the effective stress condition. Or this path may touch the failure plane or may not touch the failure plane. So when you draw sigma versus tau, P dash Q dash graph, where P is sigma 1 plus sigma 3 by 2 and Q is sigma 1 minus sigma 3 by 2. We transform this Mohr circle into the path followed by the stress applied on the soil sample. Okay, it is very important to understand what path the stress imposition following, because this will give you how much amount of the overburden pressure that can be applied on the soil sample. So this is that is in the form of a major principal stress and minor principal stress, and this is in the form of a simple stresses. So here you can understand. So this is sigma h and sigma v. You take any point. So P is nothing but sigma v plus sigma h by 2, and Q is nothing but sigma v minus sigma h by 2. So either you represent in terms of the major principal stresses or simple horizontal and vertical stresses. Okay, so if you know only the major, and if you only sigma h and sigma v, and if you also knowing the intensity of the shear stresses in addition to the horizontal and vertical stresses. So that is sigma h, sigma v, and tau vh. So this is how it looks like. And here in this case, so the P and Q can be defined as, so P is defined as same sigma v plus sigma h by 2, and Q can be defined as square root of sigma v minus sigma h by 2 whole square plus tau vh whole square. So this is something like a radius of the circle or radius of the any triangular portion. So P and Q. So when you have given only the major and minor principal stresses, this is how you can able to draw. And when you have already given, so the in addition to the sigma h and sigma v, even shear stresses also, this is how we can able to draw it. So this is what is the meaning of the stress path. So let us try to understand. So we have done the triaxial testing on the soil sample, and we applied three variety of the confining pressures. So we got the three Mohr circles, and we have done separate testing at the soil sample until it is failing. Thereby we have developed the Mohr-Coulomb failure envelope. So this is Mohr-Coulomb failure envelope. Then what we have done next? So this is known, the red line is known, that is Mohr-Coulomb failure envelope. Now when we impose a load in the field, this is what the path we follow. We applied this much amount of load, then increase subsequently. So 1, 2, 3. So then we want to see whether the imposition of load 2 is above the load 1 or the right or left side of this load 1. Okay. So suppose if you join the points of all the maximum from of these Mohr circles, then we will get a line. So this line is called as a stress path. Stress path. Okay. What is the implication of this stress path here? See, try to understand. Although we started from applying the load from 1, 2, 3, 1, 2, 3. So as long as this stress path doesn't meet the Mohr-Coulomb failure envelope, there was no failure. There was no failure. Okay. So, and we also should aware, when you are applying the increase in load, are we going away from the Mohr-Coulomb failure envelope, or are we moving towards the Mohr-Coulomb failure envelope? So that's what we will understand from this stress path. Stress path. Okay. And one important thing is that, are we following the linearity or non-linearity? Are we imposing the load linearly or non-linearly? This can be understood from this stress path. So stress path is a convenient way to keep track of the progress in loading with respect to failure envelope. So a line drawn through the stress points of maximum shear stress. Hope you could able to distinguish between the stress path and the failure envelope. Stress path and failure envelope. It's quite simple. There is nothing great. So this is further understanding. So this is what we have done exactly. So initially you have conducted so many number of the triaxial test. Okay, ultimately you achieved the fail. But what kind of the path it followed? So that can be understood by joining the lines of the maximum shear stress. You try to understand. So when you join the points of the maximum shear stress of all this Mohr circle, this is what is the kind of a graph you obtained. Okay, so at this state you failed. At this state the soil sample has failed. So this is this representation is called as a representation of PQ graph or P dash Q dash. And this is the failure plane. Of course, you can also interpret stress path the values of the C and pi. So the C and pi can be interpreted from normal versus shear stress diagram, P dash Q dash graph. So when you are interpreting the C and pi from the PQ graph, then so the that is the ordinate value is C cos pi, and the pi value is tan inverse sin pi. So tan inverse sin pi. So tan inverse sin pi. This theta, this some value. So from this theta value, we can able to determine the pi value using this equation. This is C cos pi. C is equals to cos pi, and C equals to cos pi. And this is this intercept, this ordinate, and this theta is nothing but tan inverse sin pi. Theta can be determined from this slope. So from this slope. So here you can see. So there is another way of interpretation. That is, when you join any tangent point of the Mohr circle with the horizon of the normal stresses versus shear stress diagram, what we get is called as the Mohr-Coulomb failure envelope. This is called as a Mohr-Coulomb envelope, which is defined as a line joining the horizon of the normal versus shear stress diagram with the tangent point of the Mohr circle. However, we can also draw another line. Which is from origin of the graph to the maximum shear stress where it is happening. So this is called as a F line or K line. This is typically called as a K line. Okay, so there are two possibilities. One was given by Mohr-Coulomb, another is called as a K line. Okay, so when you draw the K line, so the K line is indicative of again how or what the stress it is follows. Stress it is follows. Again here we can see. Now try to understand logically. Let me distinguish you between the previous slide and this slide. Okay. Now let us look at this Mohr circle. In this bunch of Mohr circles, we varied sigma 3 and we varied sigma 1. We varied sigma 3, we varied sigma 1. And as a result, particular stress path. One particular stress path. Now let us try to understand. I kept sigma 3 constant but increased the sigma 1. Increased only the sigma 1. Then what kind of the path it follows? What kind of the path it follows? This is nothing but when you are excavating the soil sample or during the excavation or during the consolidation, what kind of the stress path it follows? What kind of the stress path it follows? Okay. So can anybody tell me what is the how this condition of sigma 3 is remained constant and sigma 1 increase can be achieved?
So by applying deviator stress, increasing the deviator stress.
By applying only the deviator stress?
Confining stress is kept constant and we are increasing the deviator stresses.
Then what is the difference of this one? Here also we kept sigma 3 constant and we increased only sigma d, delta sigma d. Anybody? What is the difference between this diagram and this diagram?
So in the previous case, we are changing the sigma 3, na?
Here.
Yes, sir. Yes, sir.
Okay. And here?
But here sigma 3 is constant.
But when that is possible, that's what I'm asking question. Why in this case it is not possible? Why it was not possible in this case and why that was possible in another case?
Sigma 3 is constant because it was consolidated. After consolidation, we are applying different kind of delta D,
Okay.
deviatoric stresses. But in this case, failure and the soil was not completely consolidated, so sigma 3 is changing.
Acha. Okay. Good, good, good. So any other logic?
The changing of the pore water pressure.
Changing of the pore water pressure. No, nothing to do with that, right? This is very simple. Why you are taking? See, here how many number of samples are there in this diagram?
So 9.
So this diagram was developed based on the 9 confining pressures and 9 variety of the samples. Is it true?
Yes, sir.
Now in this case, how many samples?
Only one.
Exactly.
One.
Okay. In this case, only one. In the previous case, it was a different samples. In this case, so on same soil, but we compacted to different density, or we compacted to same density, but applied the different confining pressures and different deviator stress, how the stress follows a particular path. Now here, during the testing itself, when you sigma 3 is kept constant and when you are increasing the deviating stress, what kind of the stress it follows, or what kind of the path it follows? What kind of path it follows? Hope it is clear to everyone now. Okay, so this is on a single soil sample. Sigma 3 is constant and you are keep on shearing the soil sample. Keep on shearing the soil sample. Now this pressure, because here if you do not measure the pore water may be different. If you measure the pore water pressure, this may be different. How? When you are increasing the delta sigma, if it is only in the form of a total stress, so this is the Mohr circle. But if it is transformed from total to the effective, there should be shift to the horizon, shift towards the horizon. That means the stress history diagram for total stress is different and the stress history diagram for effective stress is different. So this point is clear to everyone now. So if you look at this diagram, so is it okay? Is it understandable?
So, sir, for the same kind of material, stress path will always be linear.
Yeah, but may not be. That's see here it is shown as a linear, but this linearity is again pertinent to the total stress analysis.
Okay.
This linearity may belong to only the total stress. Suppose for the same sample and for the same imposition of the delta sigma d, if you draw the same thing for effective stress analysis, would it be linear? Maybe or may not be. We do not know.
Okay.
That we will try to understand. So, so this is this is P dash and Q dash in terms of the effective stresses. So this is total stress and effective stress. Total stress and effective stress. These are the P dash and Q dash. So sigma 1 minus sigma 3, sigma 1 plus sigma 3 by 2. So this is sigma 3 dash plus delta sigma 2 plus delta sigma 3. So this can be written as in this form. That is and Q dash in terms of effective stress. So this will become only delta sigma d by 2. So your if you write P dash in terms of the effective stress, that is sigma 3 plus delta sigma d by 2, while Q dash is only delta sigma by. So this is some observations. Each successive plot of P dash and Q dash will continue this straight line, that is 45 degree with respect to P dash axis. But if you done on only one sample, eventually we will reach the point D. This is the point D, and the Mohr circle B, and the sample fails. So it has reached the modified failure envelope. So here see. So the meaning of this one is, when you are trying to correlate the shear versus normal stress, we are always looking for the point of the tangent, where the Mohr Coulomb failure is touching the tangent of this Mohr circle, But so the failure can also happen. When the stress path is meeting the peak point of the stress. So when stress path is reaching point D, so the soil sample is failing. Okay, just try to imagine. Earlier we were dealing with the point of intersection, but now the new stress point has arisen. That is point D. point D. Okay, so the sample at which it fails, and if you try to join this origin with the point at which it has failed, then this line is called as a K line. This line is called as a K line. This is Mohr-Coulomb failure envelope, and this is called as a K line. This is called as a K line.
Sir,
Yeah.
sir, here in this diagram, which this Mohr-Coulomb failure diagram which you showed, sir, we are reaching D after which the failure takes place by Mohr.
Yeah, at D failure takes place.
No, so D is we are reaching D after Mohr failure.
No, below. You can see this is above. That's why two separate lines has been drawn. Na?
No, so the tangent is touching the circle well before D touches the circle.
Yes, that's what I mean to say.
So it will be the case always.
Yeah, it will be the case always.
Okay, sir.
It will be the case always. That's why we need to understand the stress history.
Okay, sir.
See, earlier, what we are saying is, say for example, in this diagram, we have. So earlier, what we are understanding is, we have conducted so many. We have taken so many number of soil samples and keep on conducting the triaxial testing until we are reaching the Mohr-Coulomb failure envelope. So this is a bit cumbersome process. Okay, bit cumbersome process. But the same thing can be interpreted once you are doing this kind of analysis. So when you go for the stress path analysis, it is quite easy to understand where exactly it fails.
Okay, sir.
Okay, so here Q dash is nothing but P dash into 10 alpha. This is the relationship between P dash and Q dash. So there is another line. So when you transform the Mohr-Coulomb failure envelope into P dash Q dash graph, so I think I will stop because it's already 10:53. Because if I start this one, then we may miss again several things. Okay, so I will stop it here. So this lecture I will cover it maybe tomorrow. Okay, so one small announcement. Last Friday I have not taken the class, and similarly on another day I have not taken a class. So I have to cover 2 extra classes. Can I take 2 extra classes 10 to 12 of this Saturday? So I'm planning to take these 2 extra classes on this Saturday. So 10 to 12. Is it okay?
Okay, sir.
Okay, sir.
Okay. So then
Yes,
fine.
sir.
So we'll be scheduling 2 additional classes on Saturday. Most likely we will try to take some kind of a tutorial on shear strength, pore pressure parameter, this stress path, so on and so forth.